Good afternoon, everyone, and welcome to the EOL seminar series. This is the last seminar of the year, and it is my great pleasure to welcome our speaker, Dr. Paquita Zuidema, who is a professor and the chair at the Rosenstiel School for Marine, Atmospheric, and Earth Science at the University of Miami in Florida. Dr. Zuidema started her schooling in physics and civil engineering, and lucky for us, transitioned to a PhD in atmospheric science at the University of Colorado in Boulder. Since then, she has made a career of gathering and analyzing cloud-relevant observations and evaluating their radiative impacts, along with cloud process modeling studies. Her recent field campaigns include being the principal investigator of LASIC, which stands for Layered Atlantic Smoke Interactions with Clouds. This campaign deployed the ARM mobile facility at Ascension Island. Paquita was the co-investigator for the NASA Oracle's aircraft campaign to study aerosol cloud interactions in the Southeast Atlantic, which brings us to her seminar, in which she will talk about processes underlying smoke and cloud interactions over the South Atlantic. We are using Slido to pose questions, which you can type in at any time during the seminar. The Slido window is located below this presentation screen. We archive all questions until the end of the speaker's presentation, where they will be revealed during the Q&A portion of the talk. Dr. Paquita Zuidema, welcome to EOL. The virtual stage is yours.
All right, thank you. You can hear me fine?
Yep, we can hear you great.
Okay, great. Okay, well, thanks so much for the invite. I enjoyed putting this slide set together and getting to kind of reflect back on these various campaigns and where we are now, and also on the role that NCAR played in these campaigns. It's not obvious from the slide, but you'll see it popping up. So yeah, I'll come back to this and I'll just, let's see. Okay, there we go. So yeah, what can we learn from these field campaigns? And a reflection. This is kind of a picture of what that stratocumulus deck looks like. There's so much smoke over the low cloud deck there that you can almost barely make out the clouds underneath it. So what motivated these campaigns? Well, this is, I guess, already showing that a little bit. But here, okay, yeah, what motivated these campaigns? What's special about this region? Why did it need in situ measurements? Are those made possible by these platforms? What do we now know? And what is still left to do? Thinking about the motivation for this, it's NCAR played an important genesis role in this, in that there was this very, I thought, successful vocals regional experiment that took the NCAR C-130 plane to the Southeast Pacific in the fall of 2008. And one of the motivating questions for the C-130 at the time was to try to understand this open-celled, they call them POCs, pockets of open-celled within closed cell regions, where you have this dramatic change in cloud albedo as you go from an overcast to a more open-celled region. So the C-130 had the strategy of flying back and forth across that boundary. This was 2008, so then afterwards, people are analyzing their data. It takes about 4 years to get to kind of chew through everything that's been collected. And you take a step back and a larger view. And US CLIVAR helped support this working group to kind of synthesize the observations with modeling foci on these eastern tropical basins. And when you do that, then the Atlantic kind of pops out. It's very similar in a lot of ways to the Pacific, to the Southeast Pacific, but not quiet. Like in the bottom, you can see the annual cycle and sea surface temperature, lower tropospheric stability, aerosol, and there's cloud fraction in there, and it doesn't really map quite as neatly onto, say, stability as it does in the Southeast Pacific. So one of the science team meetings was held in Miami, and that was like right before a climate supported workshop that looked more at the Atlantic at the same time. So the idea of going to the Atlantic was starting to bubble up then. Then that summer, there was a CloudSat Calypso meeting that happened to be in Paris. And at that meeting, there was a lunchtime gathering of about 10 people where the conversation kind of turned to the aerosol optical properties. It was, more remote sensing expertise, and more people interested in the optical properties. And that's kind of where I think the real where the idea of proposing to go to the Southeast Atlantic really started. Jens Redemann was there from NASA, and he got very interested in leading the Oracles campaign. And there were people there from the UK, Jim Haywood and France. And we kind of left this meeting and started an informal email exchange that kind of kept things going. And it also helped that there had not been a significant campaign in the Southeast Atlantic since Safari in the year 2000. So it had been over a decade, and importantly, Safari happened before all the A-Train satellites were up, like the Calypso CloudSat. So it didn't really serve to validate the remote sensing algorithms that people had developed. So the main, but that's kind of more the sausage making. And then the main science driver was something that came out of the AeroCom community, where they did a model assessment of global aerosol models, and it highlighted this little bullseye of warming in the Southeast Atlantic. You can see it in this panel in the upper right hand, labeled B, red circle around it. So a little bullseye, but if you look at individual models shown on the left hand side, there's actually a wide range of top of atmosphere radiative forcings, really, depending on the model, including the US models. So they actually are spanning the range shown here with the NCAR CAM5 model in the bottom right, and the NASA GMO model in the upper left there. So there's different reasons for this. Single scatter albedo for the aerosol can vary, but there's also a cloud component to this, in that the large scale models have difficulty capturing these thin, low-lying clouds, also part of the motivation for vocals. So there was a lot of variation in the model cloud fraction, and that could also be contributing to this. So really, a lot to chew on, and how shortwave absorbing aerosol affects the top of atmosphere radiation really depends on the reflectivity of the underlying surface. This is just to drive that point home, but if you have dark smoke over a white cloud deck, then it darkens the scene. But if you have that same smoke layer overlying a dark surface like the ocean, then it makes it look brighter. So it's, in that sense, it's that scenario, it would be cooling the planet. So this is really like a perfect problem for cloud and aerosol scientists to go after. And this kind of calculation had already been around. So Jim Haywood and company had done this. You vary, there's various versions of this. You vary the cloud fraction or the cloud albedo and the single scattering albedo, and you can come up with an estimate of the top of atmosphere radiative forcing. So yeah, and another interesting thing was that the CMIP5 models were coming up with estimates, I don't think you can see this, of less than 5 watts per square meter over that region, but there are already some satellite-derived estimates that also have their own issues, but they were far larger. So that hinted that not only do models have difficulty capturing the sign, but also the magnitude may be way off. Okay. So perfect setting really for direct observations. Unknowns that are not, you can't get at with satellite, so you have unconstrained models. There's many fires that are set on the continent there. I'll back that up with some more slides. And the emissions are not like what you see in the northern hemisphere. You have this large low cloud deck. And you also have an interesting meteorological coupling over what's a much smaller oceanic basin than you have in the Pacific. So I like showing this because, wildfires are getting a lot of attention in the US and, certainly out west. You're seeing them in Boulder. And so we're getting a sense of a taste, I think, of what it's like in Africa, that even though we do have wildfires in the northern hemisphere, it's still only about 15% of the global fire emissions. In Africa it's more than 50%. So 3 times more than what we're experiencing in our neck of the woods. So it's almost hard to imagine, the slurry of smoke that's existing there. It's a different fuel type than what we have in the US, less woody. My understanding of it is that a lot of it is these grass covered woodland savanna regions where the wood shrubbery has become fire resistant over time, and it's mostly the grass underneath that burns. It's mostly set by humans, not so much by lightning or natural causes. And I think this is a nice paper that drives that home. It looked at weekly cycles, and there's fewer fires in the weekends, and Christian and Muslim regions have different off days for when they're doing their burning. So that was kind of clever analysis, I thought. That there is pollution over the remote southern hemisphere was first kind of recognized from satellite analyses of when people were trying to get a better handle on the ozone hole over Antarctica, and then started to notice that there was tropospheric ozone over the Atlantic, and that was not expected, given that the southern hemisphere has less land and fewer people than the northern hemisphere. And then they used ozone sondes over Africa and Ascension Island to attribute it to biomass burning in Africa. But how that smoke was getting out over the ocean was not known so well. And one thing, piece of work that my student Yemi Adebiyi did that I'm kind of proud of, is that he took a bunch of high split trajectories and connected it to the driving meteorology, which is this wind isotac that develops when the Kalahari Desert heats up, and you get a strong temperature gradient with the more moist equatorial forests, and that sets up a thermal wind that is strong enough that it actually turns into this wind isotac called the African Easterly Jet South. Sharon Nicholson was the person who first identified that. So it's more explicit than land meteorological coupling than you get in the Pacific. So I can't see you, but you know, this is like the I don't know, the flagship data from the A train. That you have the space-based LiDAR that gives you the aerosol extinction, aerosol profiles, and CloudSat gives you the cloud vertical structure. You can do a lot with that, but there's still some missing key pieces of information when you put together these kind of analyses. And that has to do with this interface between the aerosol and the cloud. So remaining questions are, you know, how often is the smoke getting into the boundary layer and interacting with the clouds, either microphysically or radiatively? And what is the smoke doing to the lower troposphere? Is it making it more stable, which will also impact the clouds? So that's kind of what you need these characterizations for, that you can really only do by actually going out there. So here's the, you know, there's overview papers on these campaigns. They're collected in a special issue of the Copernicus ACP Atmospheric Chemistry and Physics Journal. The NASA campaign, yeah, Jackie mentioned it, the oracles. So that went out 3 months from 3 different years. The French and South Africans had, the acronym was Aeroclo, that was mainly based out of Namibia. The UK campaign was called Clarify, and then the DOE LASIC campaign. They all had common objectives, you know, to improve knowledge of the aerosol properties of the smoke, get a better handle on the aerosol cloud vertical distribution, and then understand how the cloud adjustments occur to the aerosol and work their way into the radiation. Yeah, so there was a lot of benefit from the synergism of these campaigns. The way, especially the way they were distributed both in space and in time. The DOE campaign went out there the first they got their deployment started in June of 2016 and was out there for 17 months. And then NASA brought 2 planes to Walvis Bay in Namibia in September of 2016. And scientifically, so that was, you know, kind of at the southern end of the, well, that's one boundary, I guess, of this whole region, and Ascension is another linchpin there. The Walvis Bay deployment was really successful from a science point of view. They did a bunch of flights. The green ones on here are the ER2, which can fly a little further, and the other ones were the low flyer P3 that was doing all the in situ measurements. So that all went well. Some cool, you know, some cool measurements. This high spectral resolution LiDAR made, you know, just beautiful aerosol imagery of the vertical structure. You can see when the aerosol is touching the clouds or when it's separated, and that's a really crucial piece of science to know, you know, if it's actually able to interact. So then you could take that information and make these composites. So the aerosol extinction, I should mention that these are valuable because with CALIOP, the space-based LiDAR, it typically cannot see all the way to the bottom of the aerosol layer. It just gets too attenuated. There's too much smoke there, but the HSRL could do it. So we have these nice extinction profiles, and then situ plane gathered statistics on when the aerosol and the clouds were made contact. So you can see that in the cloud droplet number concentration. So that was really great new information. multiple measurements of the single scattering albedo, which is a difficult measurement to make. The oracles values on here are they have the bigger squares and the bigger symbols on here. The key one to pay attention to is the green line with the diamonds. Those are the in situ values that are kind of the reference. So that's nice, and that let us know that the single scattering, the smoke was a little more absorbing than people had originally thought. So you can go back to a calculation like this and already kind of estimate, oh well, this will increase the warming that you would see in the atmosphere by about I don't know, 5 to 10 watts per square meter or so. So that was all good. The part that did not go so well was the politics. You have an ex-submarine hunter plane out there, the P3, this ex-high altitude spy plane. So yeah, what could go wrong? Well, the media really picked up on this idea that these were ex-spy planes. And these are, I have some statements here that I screenshot from the Facebook page of this Namib Times, but just a lot of suspicion and discomfort with us being there. There actually was one sane comment that I also included on the bottom here that was heartening. And something to point out too is that NASA has they have a harder time getting the permits to fly than NCAR plane would be, as I understand it, because the NCAR C-130 is certified to fly out of just about any airport, I believe, in the US, whereas the NASA plane has to, because they outfit the planes differently for each campaign, they have to go through that process anew for every endeavor that they make. So Oracles did not, they had planned to come back in 2017 and 2018, but they were never able to get the permits to do it. So there was kind of a hard pivot to go somewhere else, namely Sao Tome, for the following 2 years. That had to happen on a pretty short time scale. And NCAR also, EOL, also played a role in this, because there had been a site survey to Sao Tome by Brigitte and John Cusack and I in 2015. And the NASA people were able to, they made a lot of use of this site survey to be able to get their own, to develop new plans fairly quickly and go to Sao Tome instead. So we're still very grateful to EOL for that. So these show, let's see, so yeah, went to Sao Tome, and actually from a science point of view, that turned out to be pretty good, because that way we could sample this large region coming in from the north rather than from the south, and that gave us a different perspective. It also included a what's called a suitcase flight out to Ascension Island, where the UK plane was based. So that was also good. So yeah, 2017 was really the busiest year with all the campaigns working at that time. I wanted to put up the instrument list for the DOE campaign. Nothing really dramatic, or I don't know. This is mostly pretty conventional, I think, instrumentation. The big value of that surface-based deployment was that we realized that smoke is much more prevalent in the boundary layer than was originally thought. And it was really nice to have the 2 years to throughout the biomass burning season to repeat that, to show that that was repeatable. Documenting the lower single scattering albedos, which were also, and this is from these filter-based measurements that people criticize, but there are other kinds of absorption measurements out there that corroborated these. And could also look more at the aerosol cloud interactions, because there was just more data to do a more of a statistical analysis on it. So Jinghao Sheng, this was his PhD work. So that helped us understand the difference in the cloud annual cycle of the two basins, and how when the smoke is in the boundary layer, then it acts to raise the temperature and burn off some of the clouds, so to speak. An idea that I think Andy Ackerman and company and Brian Toon kind of showed much earlier. And when, whereas when the smoke is in the upper atmosphere, then it helps to support the cloud layer. So that was important. So yeah, the LASIK measurements were valuable for that. Given that this is EOL, I also wanted to show the instrument list for the Clarify aircraft deployment. And here what I do have highlighted on here are these absorption measurements by something called the Excalibur, where they had 3 different instruments, and in particular something called the cavity ring down spectrometer, that from which they were able to get very accurate absorption and extinction measurements at both dry and humidified conditions, and free from the biases that filters end up running into. So something that was critical for trying to stitch all these campaigns together was to do an intercomparison, and that was bravely led by Paul Barrett. The NASA plane flew out to Ascension, and there was a very dedicated intercomparison flight that has proved to be highly valuable. So it's not glamorous, but it's important to do that. And that also gave these opportunities to combine data from the different campaigns. This was a very creative study led by Michael Diamond, where he took Oracle's data from a routine flight along 5 East, and then used trajectories to connect it to measurements made around Ascension, and combined it with a modeling study with fires, without fires, with radiation, without radiation. And a main thing that came out of that was that when you have the shortwave absorption from the smoke also helps loft that smoke layer when it's in the free troposphere. So it's the dark red line on panels A and B. So that will change where the smoke ends up entraining into the boundary layer, and kind of strengthens that stabilization of the free troposphere. Yeah, we had long discussions on how to compare observations to models, because even at best you still never have enough observations for the model comparisons. But we did follow this routine flight plan idea, which was inspired by the Vocals campaign, where you just repeat certain flights a number of times and try to get representative statistics that way. So what's left to do? Okay, good. I was worried this talk would be a little long, but I'm doing all right. We still are doing, I mean, you'll have noticed that a lot of those papers have just been coming out this year or last year. There's still more work to do to integrate the, what we're learning about the aerosol processes into the models. overall, also because of the boreal fires in the Northern Hemisphere, I mean, there's just a lot of attention now on wildfire processes. So for anybody who's interested in that, I think it's pretty clear that it's just better articulated now than it was even, say, 5 years ago, 10 years ago. A lot of that analysis, though, is still near source, meaning, near where the fires are happening. Like in the US, you'll see, people will identify individual fires, and they're able to follow the plume and analyze that data as a function of time from emission. Whereas in the Southeast Atlantic, you really can't do that. It's kind of a slurry of smoke. There's just so much of it, and it's all kind of combining. So there's some loss of the source memory in that. And B, by the time it gets over the Southeast Atlantic, it's at least 4 days and more like a week old. So it's just in kind of a different regime. Kind of interesting, I think, is this left-hand plot. This is a relatively new plot that my student Amy DeBrocchi is including in her as part of her PhD thesis. But this F44 is, well, both of these are measures of chemical markers of aging. And you can see that the smoke that reaches Ascension Island is a little older, according to these metrics, than what was measured by the Oracles campaign. It makes sense, but that it actually shows up in these metrics is nice. Art Sedlacek has just recently come up with a paper where he's examined coating loss. So black carbon becomes coated with a lot of organic aerosol as it in the first couple days. From gases condensing, smaller particles coagulating, but then it starts to lose that coating. And we don't have very many solid measurements of that, but he has them here, and also comparing them to some loss rate coefficients that were derived in labs, and they don't really match either one of those. So yeah, more to do to make, ultimately we would like to inform or bring it into these global aerosol models and arrive at more of a consensus view of what the regional radiative forcing should be for this region. This is a nice paper by Marc Maillet, just came out last year. He's looked, a bunch of these will be CMIP6 models, and kind of organized them by biases in both aerosol and clouds. And it's not, I forget how this compares to CMIP5, but there is more work to do there. So something that we're finding is that there's a very good correlation between the single scattering albedo and this organic aerosol to black carbon mass ratio, which fits in well with what Art Sedlacek has been finding from his coating thicknesses. So there was a DOE ASR meeting about a month ago, and at that meeting, Art Sedlacek, Yangfeng, and we wrote a white paper to propose a workshop on to look at fire emission issues. There's already been a couple in the US, but we think there is, looking at the more aged regime would be valuable. And yeah, this is, if we're able to hold this workshop, I would expect to advertise it widely. So, okay, thought question: can we expect large-scale models to correctly capture this regime, since CMIP6 isn't quite there yet? It seems, this is just my view, but it does seem to me that by CMIP7 we might actually be there, because I do think that that this representation of the single scattering albedo, and we'll have a better handle on it by then. Work has been, the low clouds have, their representation has been improving over time. And also I mentioned in here the representation of the large scale subsidence. So there is this issue that the subsidence tends to be overestimated in this region in models. So they tend to just drive the aerosol too quickly into the low clouds. So how to fix that, I don't quite know, but it's given that it's a large scale issue. I hope, well, I'm sure work will continue on that too. So it is kind of, it's just a region, and I do get the feedback sometimes that maybe it's kind of provincial given the global, it's not, is it really impacting the global mean state? I guess the best argument back I have is that improved prediction of rainfall is a #1 priority, especially for arid regions. There's kind of a trade-off between how much heating in the atmosphere you need. If you're, well, this is a nice paper by Angie Pendergrass. If you have more heating in the atmosphere from smoke, black carbon, then there's less latent heating release to balance the energy balance of the Earth. So in that sense, it's important to try to get that right. I want to, so by way of acknowledgements, I do want to say a lot of the work has been led by the students here in Miami. And I also want to give a shout out to Mumpy Sarkar, who I think might be in the audience, who was involved with the CSET campaign that was right before these campaigns, and was also privy to a lot of the conversations about this area. And of course, this really requires like a village of people to make the whole thing work. So with diverse skills and talents. So I want to bring that out too. So I think that might be my last slide. Let's see. Let me see. Yeah. So I'll just back up there and take any questions. And thanks for attending. Should I stop sharing my screen?
Oh no,
or...
you can keep your screen up. Brett will handle that.
Okay.
But thank you, Paquita. It's nice to see the evolution of the cloud and aerosol research over the Atlantic since your interest in the field, and what has motivated your research. We have time for questions or comments, so may I remind the audience to please use the Slido interface below the presentation screen to ask your questions. So hopefully, Paquita, people are judiciously typing their question. But in the meantime, it's hard to imagine that wildfires and biomass burning haven't increased globally in the past decade. With the recent campaigns that you've led, have you found evidence of increasing or more intense fires that could change how we understand cloud aerosol interactions and how we model them?
Well, okay, so there have been papers coming out that show that yeah, there's less burning of forests, and so that's and that's, I think that's true everywhere except Southern Africa. Well, there isn't much forest there, but the grassland burning is still continuing. And there, what I would expect would happen is as the world gets warmer, this Kalahari heat low becomes more pronounced. It's already a hot desert, but that would strengthen these winds that transport the aerosol off of the continent. And if you have a hotter continent, it also puts those winds at a higher altitude. So there might be a shift in how much of the aerosol is close to the boundary layer and how much is residing in at like 5-6 kilometers. That's where these winds are happening. They're pretty high.
Okay.
So yeah, does that answer?
It does.
Um,
To a certain degree, but I have a follow-up question. But then we have a question from Vivek, and he says, thanks for the great seminar. Could you comment a bit more on challenges related to correct representation of marine low cloud deck?
Oh, well, so as the resolution increases of the global models, and now there's like global models at 3-kilometer spatial resolution, and there's an effort in Germany to go to even 1 kilometer. I would expect that increase in resolution alone would do a lot with improving the low cloud coverage, because you would have a higher vertical grid spacing, and that would let you resolve the thinner clouds more readily. So I guess that's an easy answer. And then, I mean, there has been a lot of effort made into the microphysics, and that's still continuing. But there's a lot of people working on that, and maybe also because of the interest in marine brightening. So I may have exaggerated. I mean, I'm sure it won't be all solved by CMIP 7, but a good example is the GIS model. So it used to not have very good low clouds, and then they just made an effort to improve all of the parameterizations, and now it does pretty decent. I wish I could see people's faces.
You could look at mine, Paquita. Pretend I'm Vivek. I was like
Okay.
a poor person's Vivek. Thank you for that question, Vivek. We have a question from Mike Dixon, who asks, has the recent increased fire activity in Australia had a significant impact on A, aerosols, and B, CO2?
Oh, that's an interesting question. I don't know. People have, those fires have been reaching really high. So it's been putting more material in the stratosphere. These African fires don't reach that high, so that's an important difference from the two regions. But I have to, other than that, I don't really know that much about these Australian fires.
Great, that's a good question. So what is the future of field campaigns in that region? Are there plans for future missions to provide continuity for these observations? It seems repetition is important from what you show from some of the studies that do.
Yeah, that would be wonderful, but the combined cost of these campaigns, I don't see it. This was a pretty big effort, right? The NASA campaign was 30 million. The DOE campaign about 8 million. I doubt that people will go back to this area anytime soon. But one thing that I do think has potential are some smaller campaigns that are quite focused. Like I could think of some more specific science questions that could be addressed by just 1 or 2 instruments out at Ascension Island. For example, we don't know how much the clouds remove of the coating of the black carbons versus
Mhm.
photochemistry. And you could put an instrument out there that measures a marker for aqueous phase processing. So maybe somebody will get motivated to propose that.
Oh. Maybe something that EOL can participate in.
Yeah, I've certainly thought about that, because NSF did not participate in this multi-campaign, and part of that was that people with the relevant expertise were busy on the campaigns that were already happening.
Yeah.
So maybe if there's a lull in wildfire research, then
Yeah.
a small campaign going there.
We have another question from Vivek, who asks, did you collect droplet spectra as in vocals? Were they analyzed using cloud radar and HSRL?
Yeah, so there was this APR3 radar from JPL that it was kind of under development at the time. So I think every year there was a slightly different version of it. One difference, though, from the Southeast Pacific is that these clouds were really, really thin. And because they were polluted, the droplets were small. So there is radar data, and Tristan Lecuyer and his student analyzed it. But I don't think it was super easy to analyze, just because even when you have a aircraft-based radar in this regime, it's still a little hard to pick up the very thin clouds. So there was yes, and there were in situ cloud probes. So there is analysis of the droplet spectra, and that was done by Greg McFarcar.
Mm-hmm.
So, there's some nice papers out on that.
Vivek says, thanks.
My pleasure.
So with no further questions, we're near the seminar hour. If you're interested in Dr. Paquita Zuidema's presentation and have further questions, please reach out to her via her email, which is provided on the seminar flyer. On behalf of EOL, I would like to thank Dr. Paquita Zuidema for her talk on observations of aerosol cloud interactions over the South Atlantic. Thank you, everyone, and have a good day.
Great. Yeah. Well, thank you for having me.